I hope everybody recalls where we have stopped last class. This is high frequency response we covered in the last class, and we talked about the capacitances that are creating problem during high frequency. The capacitance such as gate source capacitance and gate to drain capacitance, they impose problem when input signal frequency is very high. That is the reason gain drops at higher frequency, whereas lower frequency this CGD and CGS will act like an open circuit, but at higher frequency they tend to behave like a short circuit and ceases the operation of MOSFET here. Okay. So, we have discussed that in the last class, and we have written an equivalent circuit of common source amplifier, okay, and simplified equivalent circuit. Finally, we have shown that the equivalent capacitance also, and then we arrived at frequency of oscillation, high frequency upper cutoff frequency expression we have derived, which we said it is equivalent to 1 by 2 pi times input capacitance and R dash signal. Okay, so, this we have discussed in the last class, the derivation part. Okay. And finally, we have shown the gain equation, overall gain equation V naught by V signal, and its frequency dependence also we have shown. The response of high frequency response of common source amplifier is as plotted as shown here, by taking overall gain along y axis and the frequency of oscillations along x axis, and the response is plotted, and we can also see the higher cutoff frequency by decreasing the mid band gain by 3 dB, we can obtain the higher cutoff frequency, and the expression for the higher cutoff frequency is as shown here. Okay. So, higher cutoff frequency now it depends on various factors, okay, especially the signal resistance, okay, AC signal resistance. Larger the AC signal resistance, upper cutoff frequency decreases, and vice versa also it is true. Okay. So, lower the signal resistance, higher cutoff frequency keeps increases, and we have shown the input capacitance expression okay, also, which is CGS plus this CGD times 1 plus GM into RL. There is a scaling factor here which increases the gate to drain capacitance due to the Miller effect here, and Miller effect is in fact a drawback. Since why this Miller effect came into play in this circuit is because if you look at an equivalent circuit, there is a capacitance that connects both input and output. Okay. Due to this, the Miller capacitance comes into play, and according to the Miller's theorem, we have to divide this capacitance. This capacitance get part of this capacitance goes to the input side of the circuit, and remaining goes to the output part of the circuit. That is what Miller's theorem states. Okay. And when we see the equivalent capacitance at the input of this common source amplifier, we came to know this is the expression here, CGS plus 1 plus GM times RL dash into CGD. Okay. And this is related to the higher cutoff frequency also, as we can see from the higher cutoff frequency expression here. Okay. Lower the input capacitance, higher will be the higher cutoff frequency, and lower the signal resistance, AC signal resistance, higher will be the upper cutoff frequency. Our aim is to increase this higher cutoff frequency. Any circuit with higher cutoff frequency is always advantage for us, but here the problem is input capacitance, and if we observe the input capacitance expression here according to the Miller's theorem, it depends on CGS and as well as CGD, and among these two, CGS and CGD, CGD is the dominating one. Reason is it is multiplied by the scaling factor here. Okay. That means this circuit, common source amplifier circuit, as a disadvantage of it has a Miller effect, and if we can prefer other circuits which can provide other configurations which can provide larger higher cutoff frequency, that will be the best circuit I should say here, best configuration I should say here. However, common source amplifier suffers from the Miller effect here. So, there is no zero Miller effect, but there are other configurations which provide zero Miller effect. So, such configurations are preferred here. With that things recap that we have covered in the last class, we will move on to the today's topic, which is an oscillator. Okay, oscillators. Okay. So, if you look at syllabus, this is the last chapter of module 2. Okay. We have started with the amplifier circuits, and later we have discussed the frequency response, and finally we end up with an oscillators in module 2. Now, let us try to understand what do we mean by oscillator. A simple definition is an oscillator is a circuit which basically acts as a generator. Okay. It is a generator because it generates an output signal which is an oscillations basically. Okay. An oscillations. The oscillations that are produced from the oscillator circuit has got constant amplitude and constant desired frequency. The frequency of our interest can be designed from the oscillator circuit here. However, the amplitude is kept constant here. This is the definition for the oscillator circuit. The oscillator circuit can be looked in terms of a block diagram here with an input signal and output signal. In fact, oscillator does not have any input signal, though I have written here an input signal is a DC here, but oscillator does not expect any a sinusoidal or AC kind of input signal. DC is required to energize the components in the oscillator circuit. Other than that, in fact, this is not an input signal at all. Okay, so this is required only to energize the components within this the oscillator circuit here. So, oscillator is a circuit without any an AC input and produces an oscillations of different sorts. Example is sinusoidal oscillations, as you can see here. Triangle kind of oscillations you can see here. We have shown here only one cycle, but these circuits produce repeated kind of oscillation. That is why its name is oscillate. Okay, this is one cycle. It keeps on producing repetitively these kind of cycles here. Okay. So, these oscillators are used in many electronic circuits also. You can see here the sawtooth waveform here. So, like this we can generate a variety of oscillations using oscillator circuits. Okay. So, now we have understood the definition of oscillator, what it is, and it is basically a circuit which produces an oscillation or frequencies of desired with a constant amplitude, and output of the oscillator circuit is generally an oscillations. Okay. And let me talk about the details of this oscillator circuit. Okay, what it is made up of, what are the components of the oscillator circuit, that we will go through step by step. Okay. Now, once we say if we need to focus on the oscillator, we need to understand the term called as feedback. Why, how this feedback is related to the oscillation. So, there is no we can't design an oscillator circuit without a feedback. So, I should say that feedback is the backbone of oscillator. Okay, what kind of feedback we will see, we will discuss that in detail. So, feedback, okay, we will see the definition of this feedback, and later on we will connect this feedback term to the oscillator. Feedback plays an important role in almost all electronic circuits. Even in physical world also you see feedback everywhere. Probably if there is somewhere loudspeaker is played okay, through the mic, you will see the feedback okay, in reality, okay, because the sound speaker produces some sound, and that in turn goes to the mic and it gets amplified. This is the best example for the feedback circuit. So, not only in the audio system the feedbacks are used, but in everywhere, in most of the electronic circuits the feedback system is used. Okay. You will come across in various courses also where all the feedback is employed. Feedback, it is almost invariably used in amplifier, okay, to improve its performance and make it more ideal. Probably if you have studied the amplifier circuit, you have to study two types of amplifier circuits. One is with feedback and without feedback. Even in our circuit in the module 2 also we have discussed common source amplifier. If you can recall, we have discussed common source amplifier without feedback, that is without source resistance, and same common source amplifier with RS. With RS means it is with feedback, and here without RS means there is no feedback. There are a lot of problems we will come across even without feedback also. Though with feedback we have seen that gain of common source amplifier has decreased, and if you look at in terms of frequency, the bandwidth will increase with feedback. Okay, the bandwidth frequency of operation, okay, the bandwidth will increase with the feedback. Without feedback, bandwidth will decrease. I should say here with without feedback, bandwidth decreases. With feedback, bandwidth increases. With feedback, gain, without feedback, gain increases. With feedback, gain decreases. So, this is only the problem with feedback. The gain drops, but in terms of bandwidth we are going to gain an advantage. Okay, we are going to gain the benefit. Okay. So, in amplifier also we have come across the different types of the feedback, positive feedback and negative feedback. Okay. So, that is what in case of amplifiers, the feedback is used to improve the performance, especially to reduce the distortion we use feedback, even to reduce harmonic noise we use the feedback. So, in amplifier circuits also we have come across the feedback. In the process of feedback, a part of the output is sampled and fed back to the input of the amplifier circuit. Okay, so, that is the definition of feedback. Feedback means certain portion of output is given back to the input. Okay. So, that is called as a definition of a feedback. At the input signal of any feedback amplifier circuit, we will come across two types of signals. One is an input signal which you are applying to the feedback amplifier, and other one is going to be the part of the output which is fed back to the input, the feedback signal. So, one is input signal, other one is the feedback signal. These are the two inputs that we see in any amplifier, whether it is a positive feedback amplifier or negative feedback amplifier, we will come across these two types of signals at the input. Both these signals may be in phase and out phase. When I say feedback is given to the input, the feedback signal can be in phase or it can be out of phase also. We will discuss this, what do we mean by in phase and what is out of phase. When input signal and part of the output signal are in phase means the replica, okay, whatever the output is coming back to the input, if it is replica of input, then type of feedback is called as a positive feedback. On the other hand, when the signal, feedback signal and the input signal, if they are out of phase, okay, 180 degree out of phase or 270 degree out of phase, such kind of feedback is called as negative feedback. So, there are two types of feedback, one must understand. We have studied the definition of feedback and we told the feedback is generally we come across in amplifier, and feedback is used in amplifier in order to improve the performance, and later we have discussed types of feedback. One is positive feedback, other one is negative feedback. Positive feedback, when the feedback signal and input signal are in phase, such type of feedback is called positive feedback. Negative feedback, when the feedback signal and input signal when they are out of phase, it is called negative feedback. The positive feedback is mainly used in oscillations. In the beginning only I told that there is a connection between the feedback and the oscillator. Okay. So, whenever an oscillator circuit employs positive feedback, okay, we can generate an oscillations. So, positive feedback which always results in an oscillations here. Okay. Hence, it is basically used in electronic circuits to produce the oscillations of desired frequency, and circuits that produce oscillations are called as oscillator circuits. Probably in computers you might have come across the oscillator. There we do not use any variable oscillators, we use the crystal oscillator. Generally in any computer there is a crystal which will be oscillating at frequency of 3.33 gigahertz. Okay. This is the frequency which is used in generally in computers, desktop or laptop. Okay. Generally Intel CPU will produce will work at the frequency of 3.33 gigahertz. Okay. So, suppose if you have a dual core, you will have each processor with 3.33 gigahertz. Okay. So, more the cores, you will see the parallel kind of operations in the desktop or in the laptop. Okay. Each core will be operating at 3.33 gigahertz, that is the frequency of operation of desktop. Okay. So, Then let us discuss the concept of positive feedback, and let us connect that to the oscillator circuit here. The feedback is a property which allows feedback, which allows to feedback the part of the output to the same circuit as its input. Such feedback is called as a positive feedback. Whenever the positive feedback is fed back to the amplifier, as its input, if it is in phase with the original input signal, okay, so that can be called as the positive feedback. And here let us take an example of this diagram what you are seeing here. There is a, in this example, block diagram example to illustrate positive feedback, you have considered here a non-inverting amplifier. It can be an op amp based, or it can be a transistor based a non-inverting amplifier. The reason why it is called non-inverting is because the signal what we give here as an input, which will not get invert here. Okay. That means both are in phase. So, V naught here and Vi, they are going to be in phase. So, as you can see here, the signal which is sinusoidal is applied as an input, that is Vi. Okay. So, you can see the positive going and negative going signal here, this is sinusoidal, and same signal is produced here replica with an increased signal strength. Okay. But phase has not changed when you see here and when you see the output signal here. Okay. This is an input signal for an amplifier, and this is the amplified output signal from the amplifier here. So, both are going to be in phase, because the type of amplifier here chosen is a non-inverting kind of amplifier, and it has got a gain of A, okay, voltage gain of A. Okay. So, V naught and Vi, they are related to the amplifier gain A. Okay. And this block diagram explains you the concept of positive feedback. As we can see here, there is a mixer here, okay, and there is a input signal which is applied here, and there is an amplifier, okay, basic amplifier. This can be any type of amplifier. Here you can think of okay, so common source amplifier if it is based on MOSFET, or if it is based on BJT, you can think of a common emitter amplifier, and if it is based on op amp, you can think of an operational amplifier with non-inverting type of operational amplifier also. Okay. So, this produces an output signal which is amplifies an output signal, and output signal can be seen here which is in phase with the input signal here, and part of the output signal is taken here. As you can see that a fraction of output is fed back to the input here, fed back as an input to the feedback network. This is a feedback network. Generally this is a passive network, a network of the such as resistance, and it can be a parallel resistance of this sort. Okay. It can be even, it is generally a passive network here, it can be the RC, it can be the LC, it all depends. Okay. So, it can be capacitor, it can be resistor here, it can be the capacitor here. Let me write it here. So, this is a type of feedback network generally we see in positive feedback here. Okay. So, a simple R and C can be seen in a feedback network, and the gain of this is noted as beta here. Okay. So, just notify this all these notations here. Vi is input signal, V naught is output signal, and beta is the gain of feedback network. So, beta can be the formula for this is Vf divided by V naught. V naught is the input for this, okay, and Vf is the output for this. So, ratio of Vf by V naught, that is going to be the beta. So, beta is nothing but which is feedback output by input is V naught, whereas amplifier gain is V naught by Vi, and job of mixer is to mix this feedback signal and with an input signal here. So, you can see here there is a feedback signal here and the input signal which is applied here, and these two are going to be in phase, and the type of feedback is going to be a positive feedback here. Based on observation of these two signals, input signal and the feedback signal, we can say the type of feedback is a positive feedback. Since 0 degree phase shift is introduced by the amplifier, and in this case there is no phase change by the feedback network here. Okay. So, as we have shown here, no phase change by the feedback network. So, therefore, the total phase here remains 0 degree or 360 degree, and so therefore, the output is going to be in phase with the input, and even feedback also is going to be in phase with the input. Okay. So, this is the concept of the positive feedback here. Okay. So, key point here to observe here is the phase of the feedback signal is same as that of the input applied, that feedback is called as a positive feedback here. Okay. Now, let us obtain the expression for the gain with feedback. This is an important expression which is required. Students should get familiar with this derivation, because this is frequently asked in examination, gain with feedback. So, we are going to discuss the same expression even in module 3 feedback. Okay. So, though we have we are discussing here in oscillator chapter, reason is oscillator uses positive feedback, but the main usage of this expression is in the module 3. So, there we dedicate one chapter for feedback itself, and we will study there different types of feedback topologies also. Okay. So, let us now derive the expression for gain with feedback. For this, let us consider the diagram here, whatever this diagram has shown here. So, from this you can see that the basic amplifier gain. So, this is the basic amplifier. We have chosen here non-inverting amplifier. So, the gain of this basic amplifier is V naught by Vi. So, that is written here. This is the amplifier gain. Okay. So, basic amplifier gain. So, I will write here this is basic amplifier gain denoted as A is equal to V naught by Vi here. So, this is called as open loop gain. Okay. So, once we connect this amplifier with the feedback network, it becomes a closed loop gain. Okay. So, here if you look at only the amplifier alone, so it is called A is nothing but it is a open loop gain. Okay. For the overall circuit, the input is a supply voltage which is Vs, and output is going to be the V naught. The ratio of V naught by Vs, considering the effect of feedback, which is a closed loop gain. Now, the moment we connect feedback to the amplifier, so this can be simply shown as there is an amplifier, basic amplifier, and there is a feedback network here, and we are feeding back from the amplifier to the feedback, and then it goes to the basic amplifier. So, this is input, and here we have an output. Okay. So, now this becomes a closed loop gain. Without this feedback, it is an open loop gain A that we have denoted here, and with feedback, okay, so this becomes a closed loop gain. So, the closed loop gain is now given by its V naught. In our case, it is output is denoted as V naught and input is denoted as Vs. So, therefore, the ratio of this V naught by Vs is labeled as AF here. So, the gain with feedback, AF means it is a gain with feedback, subscript F denotes here it is a feedback. If we do not mention anything in the subscript here, it is a basic amplifier gain without feedback, of course. Okay. So, AF is nothing but which is a V naught by Vs. So, output signal by the input signal. So, now let us find out the expression at the input of the basic amplifier. The feedback is positive. Okay. So, since its type of amplifier is non-inverting, the voltage Vf is added to the Vs at the Vs to generate input of an amplifier. So, if you can refer to this diagram here, so you can see here at this point here, at this point we can write expression for Vi. So, Vi will be the sum of this Vs and Vf here, because this signal, feedback signal, is also in phase with Vs. So, therefore, the Vs will get added up with Vf. So, therefore, we can write expression for Vi as Vs plus Vf. So, that is what you see in this equation 1. So, Vi can be written as Vs plus Vf. Now, we can write the expression for Vf. Vf is nothing but it is a feedback voltage which depends on the feedback element gain, which is beta. It is a feedback gain which is a beta. So, we can write now Vf as beta times V naught. For the feedback network beta, Vf is going to be the output and V naught is going to be the input. So, we can obtain by cross multiplying this Vf as beta times V naught. Now, we can substitute this equation 2, which is Vf voltage, feedback voltage, in this amplifier input expression, and we will see what expression it results, what equation we get it here. So, Vi is equal to Vs, we keep as it is this term, whereas Vf we will replace with beta times V naught. Now we can just rearrange this terms, various terms. So, Vs is taken to the left hand side as you can see here, and Vi is moved to the right hand side, minus beta V naught is kept as it is. So, now we got equation 3 which is nothing but Vs equation here. Now, we can substitute this Vs equation in the Vf equation, okay, Af equation, so which is here. So, now we get overall feedback gain with feedback as V naught divided by, this is the expression for Vs, Vi minus beta V naught. Now, to further arrive this Af in standard form, we need to divide numerator and denominator by Vi. Okay. So, let us see what happens when we divide numerator and denominator by Vi. So, now Af becomes V naught by Vi, and 1 minus you can see here Vi get cancelled here, we have left out with only 1 minus beta times V naught by Vi. Okay. So, this can be denoted as, we know that V naught by Vi is nothing but A basic amplifier gain, and even in numerator and denominator we can replace V naught by Vi as simply A. So, therefore, the final expression for Af is A divided by 1 minus A beta. So, this expression is very important, and this we will use both in oscillator topic and even in the feedback also. Okay. So, the gain with feedback is nothing but A divided by 1 minus A beta. Observe the negative sign here, and also there is a factor which is 1 minus A beta, which is in the denominator. So, obviously, gain with feedback reduces by 1 minus A beta, okay, since it is present in the denominator here. So, this is the amplifier gain, A is equal to V naught by Vi. Now, let us make an observation here to understand the importance of the feedback in oscillator circuit. Okay. So, consider various values of beta. Beta is nothing but which is the gain of the feedback network. If we take different values for beta, keeping this basic amplifier gain A as constant, say at 20. Generally, common source amplifiers or any common emitter amplifier will provide gain in the range of 10 to 20. So, let us assume that basic amplifier gain is 20, which is constant, but by now varying the feedback network gain, which is 0.05 we choose initially, the overall gain becomes 22.22. Okay, and a further increase in beta value to say 0.04, AF has been increased to 100, and you can observe here the moment we raise beta to 0.045, AF now reaches 200. Another interesting thing is when we make beta as 0.05, okay, which is exactly reciprocal of this, observe the value of AF, AF has become now infinity. Okay. What do we mean by that? So, gain with feedback, AF is nothing but gain with feedback, okay, tends to infinity. This tends to infinity when the beta is going to be very large. When beta increases, keeping this as a constant here, we are not varying here basic amplifier gain. So, keeping this as constant, and by increasing the feedback network gain beta from 0.05 to 0.05, 0.005 to 0.05, we can see that AF has been increased from a very small value 22.22 to all the way to infinity here. That means the amplifier with feedback produces an infinite gain, okay, infinite gain when the beta network has got large gain here. Okay. So, when AF increases because of increase in the beta here, and this AF becoming infinity is a limiting case here. That means, so the circuit can produce an infinite output without even input signal also, we will see that. Okay. Okay. So, the above above result shows that the gain with feedback increases as the amount of positive feedback increases. In the limiting case, gain becomes an infinite. This indicates that circuit can produce output without external input Vs. So, this is the last limiting case what we are saying here. This shows that circuit produces an output without even applying the input here. You may think that whether practically it is possible to get an output without applying any input. So, we will see that how this circuit, especially oscillator circuit or positive feedback circuit, produces an output without applying an input here, okay, because positive feedback is used in oscillator, and definitely this is the backbone of an oscillator. And in the positive feedback, as we have seen here, circuit produces an infinite gain, okay. So that means the circuit produces output without an input here, just by feeding the part of the output as its own input. So we can get the output here. Output cannot be infinity, but it it gets driven into the oscillations. In other words, circuit stops amplifying and it starts oscillating, okay. So the moment we increase the feedback gain here, what is an observation we need to make is, once this AF becomes an infinity, that means amplifying action by the amplifier is stopped and it starts oscillating here. So this is the basic principle used in oscillator, okay. So key point here to observe is, without an input, the output will continue to oscillate, whose frequency depends on the feedback network of the or the amplifier, or both. So the frequency of oscillations is depends on these three things here. It depends on feedback network, it depends on amplifier, or sometimes it also depends on both, okay. Such circuits are called as an oscillator circuit, okay. And here the two things which we need to play important role is the beta term and A beta term. That is very important here. So as we said that beta is nothing but a part of the feedback is part of the output is fed back to the input. Generally we said that beta is less than unity, but if you look at as a loop gain, okay, loop gain means it is A beta, okay, A times the product of A beta is called as loop gain here, okay. So the feedback network is basically an attenuation network or passive network, we already mentioned about this, okay. To start the oscillations, initially we need to make the product of A beta larger than unity, and but once circuits starts oscillating, the A beta, the loop gain, will adjust to the unity. Circuit itself will adjust this to unity, but in the beginning, to start an oscillation, we need to make A beta larger than unity here, okay. And later onwards, once oscillations are produced, circuit automatically adjusts A beta to 1, okay. So then onwards it produces some oscillations, and the circuit can be called as an oscillator here. There are other definitions also, as we said, the first definition here, an oscillator is an amplifier circuit with positive feedback. Without any external input signal, the circuit which produces generates an output waveform, and particularly the oscillations is called as an oscillator here. So this is a definition of oscillations. Oscillation produces an oscillations of constant amplitude with desired frequency. Even in AC source which is coming to your home, you can observe the oscillations. It is going to be typically 50 hertz, okay. You can just use an oscilloscope and observe the AC signal which is coming through the plugs, okay, will also oscillate at a frequency of 50 hertz, but this frequency is fixed in the entire country, and it depends on the other countries. So some countries they may use AC frequency of 60 hertz, especially the western part, the US and other countries, they use AC signal, AC supply, which comes at 60 hertz, okay. But there the voltage is rating is very less compared to ours voltage, okay. Ours is it varies from 220 volts AC supply to 240 volts, okay, 240 or 250 volts, but there it is going to be 120, 120 to 140 volts. Because of increase in frequency, the voltage has been reduced, okay. So therefore it is 120 to 140 volts, that is the voltage used in US and other countries, okay. Whereas in India it is 50 hertz, therefore the AC supply voltage is 220 volts to 240 volts. This is the AC voltage range, since because of frequency is fixed is 50 hertz, okay. So anywhere you measure in the country, the frequency of AC supply, AC source is 50 hertz, and voltage AC voltage is going to be from 220 to this is I am saying from normal home applications, for home appliances. This is the AC source which is provided by the supplier, okay. Okay, so that is the basic foundation of positive feedback we have seen, and but if you want to generate oscillations of different frequency, then we need to use oscillator circuit. An oscillator circuit can produce frequency from megahertz to all the way up to gigahertz. Okay, especially in microwave, microwave devices, we will see frequencies in gigahertz. Okay, especially in audio frequencies, like loudspeaker or music, whatever you see, it is going to be in low frequency range, audio frequency range. Generally, the low frequency range is called as audio frequency range. Okay, let us try to understand next the Barkhausen criteria. Barkhausen criteria is important to understand how oscillator produces an oscillation. Okay, this is also important from examination perspective. Here we are considering an inverting amplifier. As you can see, the inverting amplifier with a sinusoidal signal fed as an input and output, you can observe there is an 180-degree phase shift here. In this case, it is observed because of the amplifier type is an inverting amplifier. The feedback is basically an attenuation network, and its beta value, if I choose less than unity, so we can see that what kind of results it produces at the output here. Okay, so here you can see that this is the basic block diagram of an amplifier of feedback network. Okay, so here it is an inverting amplifier. We have preferred basic inverting amplifier which has a gain of V naught A here, and input is Vi here, and the output of an amplifier is denoted as V naught here. The part of the output is fed back to the input feedback network, which is V naught, and output of the feedback network is Vf, which is equivalent to beta times V naught, and this is going to the mixer here. A mixer combines the input signal and the feedback signal, and once again it goes to the oscillator here. So, in this case, what we need to understand here is the basic inverting amplifier. It produces 180-degree phase shift, as you are seeing here. So, you can see positive cycle and then negative cycle. So, here in the output we can see negative cycle and then the positive cycle. That means there is a 180-degree phase shift between input and the output of a basic inverting amplifier. And since we have to generate an oscillation, we need to design a feedback network such that it produces again 180-degree phase shift, because total phase shift in the loop should become 360-degree or 0-degree. So, therefore, we design here the feedback network with a 180-degree phase shift here. Okay. So, total phase shift becomes 360-degree. Now, here let us apply some the temporary voltage, which is called as a fictitious voltage, which is Vi, which we are seeing here, okay, at the input of an amplifier. So, V naught output of an amplifier circuit now becomes A times Vi. The feedback network is Vf is equal to beta times V naught, as we have seen. Now, we can substitute this feedback voltage in this this V naught in this feedback voltage expression, and we get here Vf is equal to A beta times Vi. So, here student should pay attention to this equation here. So, what is the speciality of this equation now? As you can see here now, as we are saying here in the circuit, in this block diagram of an oscillator circuit, here we are providing the feedback signal, and there is an input signal which is applied here. And here in this equation, you can see here there is a Vf, which is a feedback signal, there is a Vi, which is an input signal here. So, now the feedback signal, if it is equivalent to the input signal, what is going to happen? Okay, so, then A beta is going to become unity, right. If I assume that A beta is 1, then this Vf is going to become equal to Vi. What do we mean by that? That means the amplifier input, if the amplifier input, okay, is, or you can say that if the feedback is sufficient to drive the amplifier input. Okay, this amplifier input earlier was fed by 2 signals. Now, Vf alone, if it is sufficient to provide the complete input signal to the basic amplifier. Okay, so, that means that is possible only when A beta becomes equal to 1. Okay, so, this condition is very important. This is the first condition or criteria called as Barkhausen criterion. Okay, in the oscillator circuit, if the feedback, okay, the loop gain, if it is made equal to unity, under such circumstance what happens is the feedback signal is sufficient to drive the amplifier input here. Okay. So, then the input signal is not at all required here, the feedback itself will drive the amplifier input here. So, this happens only when A beta is equal to 1. Another thing is important is the phase of the feedback signal should be same as the input signal here. Okay, these are the two things which are required for the oscillator circuit to produce oscillations here. The second thing is, second condition is what it says is the feedback network has got 180 degree phase shift, and if the amplifier also produces 180 degree phase shift, the total phase shift must be equal to 360 degree. When the total phase shift is 360 degree or 0 degree, in such case the oscillator circuit produces the oscillations here. To summarize, there are two things which talks about which we need to talk about Barkhausen criteria. Barkhausen criterion means the total phase shift around the loop, okay, from input through an amplifier, that is a feedback network back to the input again. So, that must be equal to 0 degree or 360 degree. In simple words, we can say that total phase shift must be 0 degree or 360 degree, that is the first criterion of Barkhausen. Second Barkhausen criteria, what it says is the A beta must be equal to 1. So, we already said this, whenever A beta equals to 1, we have seen that here the feedback signal is sufficient to drive the basic amplifier. Okay, it will produce the equivalent signal similar to the input signal only. Okay, so, this happens only when A beta is equal to 1. Okay. And but in reality, that's is it possible for the feedback network to drive the basic amplifier? Okay, so, initially what happens in the oscillator circuit, initially the A beta will be equal to greater than 1. Okay. So, we apply since we apply a DC signal here to energize the components. Okay. So, the A beta initially will be greater than 1, and slowly circuit will start adjusting itself and it will tend to become 1. Once it tends to become 1, it produces an oscillations here. But initially to produce to start the oscillation, we need to have A beta greater than 1. Okay, once circuit starts adjusting because of the feedback, positive feedback in this oscillator case, so it produces a sustained oscillations here. And we will see what happens if A beta is greater than 1. So, when A beta is, when the loop gain, A beta is nothing but loop gain, and if we maintain again total phase shift as 0 degree or 360 degree, but limiting case here is A beta, if I assume that it is greater than 1, you will see oscillations of this growing type of oscillations here. Okay, oscillations keeps increasing here. This is the effect what we see in the oscillator circuit when the A beta value is going to be greater than 1. Okay. This even you might have observed in the laboratory also, while in the beginning once you apply the DC source in the beginning, you can observe this kind of the waveforms, okay, in oscillator circuit. Whenever this A beta is equal to 1, and if we are able to maintain total phase shift as 0 degree or 360 degree, as you can see here, the sustained oscillations are produced here. Okay. Another hand, if A beta is less than 1, you can see that there is decaying in the oscillations here. So, oscillations finally cease and it becomes like a DC signal here. This happens when the A beta is less than unity here. So, now we understood that what should be the A beta value in order to produce sustained oscillations. A beta greater than 1 produces growing type of oscillations, A beta equals to 1 produces sustained oscillations, a constant oscillations, and whereas A beta less than 1 produces decaying or exponential decaying kind of oscillations here. Okay. Here as we said earlier, so without any input signal, and since in the beginning if A beta is larger than 1 and circuit adjusts itself to the A beta equals to 1 with the help of feedback, and it produces sustained oscillations here. But to begin with, some starting voltage, DC voltage is required, and that produces the oscillations in the oscillator circuit. But question is whether we need any fictitious input voltage or not. Practically there is no such input is required for the oscillator. In the beginning, as I told you, the A beta must be greater than 1, and later on it adjusts to 1. And this classification of oscillators, we will discuss this in the next class, the different types of oscillators, and As per our syllabus, we need to cover two types of oscillators. One is RC oscillator, okay. So, RC oscillator, the other one is going to be the LC oscillator. Why these two types of oscillators are included in your syllabus? Reason is very simple. RC oscillators is used in audio frequency range, LC oscillators are used in, okay. So, higher frequency range here, okay. Higher frequency range or radio frequency range, okay. So, this is audio frequency and this is radio frequency. So, we need to study both the type of both type of circuits in our course. So, we will see that in the coming classes, okay. Any questions for today's class? I hope you got an idea of the what do we mean by oscillator, and we understood types of the feedback, and later on we understood the positive feedback concept, and then followed by we have understood the percussion criterion, which is important okay, to satisfy in order to produce the oscillations here, okay. So, that is all for today's class, and in the next class